going to go through this Unit 9, Worksheet 1, qualitative impulse momentum. So we're not really getting into numbers too much yet, or at least that's what that claims. So here is, this is slightly different than the equation that I gave you, than the version in the notes. Instead of force net, that's the same as unbalanced force. And here, the delta came to the outside, so that's change in momentum. The mass isn't changing, so whether you write mass times delta v or delta mass times velocity, it's the same thing. So that's the same thing that you have from your notes. All right, so how about this number 1? If you throw a ball horizontally while standing on roller skates, you roll backwards. Why is that true? It's kind of like a recoil effect, same as if you're holding a rifle up against your shoulder and you fire the rifle, bullet comes out this way, and you feel that kickback from the rifle. So will you roll backwards if you go through the motions of throwing the ball but hold on to it instead? And explain your reasoning. So the answer is no. You will not. And the reason is because the unbalanced force is 0 if you hold on to the ball. We know that Newton's third law, equal opposite force. So if I'm holding onto a ball and I throw it forward and let go, then the force that I apply to the ball with my hands is equal but opposite to the force that the ball applied to my hands. Right? There has to be. There's only one like hand-ball reaction. So if I'm pushing the ball forward, then the ball is also pushing on me backward. Now, if I'm doing that, but then I stop the ball also, well, then the stopping force of my hands on the ball is going to pull forward on me. So it pushed back, but then it pulled forward. As I change my force on the ball to stop it, the ball changes its force on me. So because in the end, you didn't change the motion of the ball, you didn't change its velocity. If you want to think about it in terms of this equation, the unbalanced force times time is equal to the change in momentum. So if the unbalanced force is 0, then the change in velocity is going to be 0. All right, we can try that too. Maybe we'll try that in class with like a skateboard and some kind of heavy ball. Which has the greater change in momentum? A 50-gram, that's 0.05 kilograms, clay ball that strikes a wall at 1 meters per second and sticks, or a super ball that strikes a wall, or same mass, strikes a wall at 1 meters per second and bounces away from the wall at 0.8. So the first one is going this way with a velocity of 1 meter per second, and then it sticks after it has a velocity of 0 meters per second. And the second one has a velocity of 1 meter per second this way, and then afterwards it has a velocity of 0.8 meters per second. So what would the mass times change in velocity be? So what's the change in momentum for each one? For the first one, the change in momentum, I'm going to write that as delta P, is equal to mass 0.05 times the final velocity is 0 minus the initial velocity. So that would be equal to 0.05 times -1, -0.05. What are the units of of momentum. Momentum is mass times velocity. That's kilogram meters per second. Easy to remember. It's just a mass times a velocity, mass times velocity. And then this one, 0.05 times, the final velocity of this one's 0.8, but I'll tell you right now, this is the number one, that's two fingers, that looks like number two. Number 11, just kidding, number one mistake that physics students make here is forgetting to pay attention to the directions of these and the signs of them. So here, if this is the positive direction going to the right, then this is negative. So the final velocity is negative minus the initial velocity is positive. So 0.05 times negative 1.8. And that's going to be a bigger change in momentum than that. I forgot to bring my calculator over. Let's see, that's going to be 18 times 5 should be, so it's negative 0.09, I think. So the bouncy one has a greater change in momentum. Right? This one, the wall just stopped it. This one, the wall like completely redirected it. That's a bigger change. And that's what we're seeing in the math there. Number 3, Hummer and a Beetle traveling at equal speeds. The idea here is this is a big car and Volkswagen Beetle is a small car. Traveling at equal speeds have a head-on collision. Which vehicle will experience the greatest force of impact? Justify your answer. The temptation here might be to say that the Beetle is going to experience the greater force from the Hummer because the Hummer is bigger. But there's only one force. There's only one collision between them. So they experience that same amount of collision, that same force, equal but opposite directions. Well, I don't know about this because this is a chicken-egg scenario, but one force because Newton's third law, or you could say Newton's third law, therefore one force, so that because can, whatever. You know what I mean. There's only one force, and so per Newton's third law, equal opposite. So same. Which vehicle will experience the greatest change in momentum? Okay, well, let's see. Force, if they're experiencing the same force, and of course, however long the collision takes, it's going to be the same amount of time. So that means they're experiencing the same force times time, right? Same force, same time, which means since force times change in time equals change in momentum, they have to experience the same. Might seem a little counterintuitive. It might seem like that, well, isn't the Beetle experiencing like more change in momentum? No, but which one will experience the greatest acceleration? Same force. So here, let's see, if we think about how much unbalanced force there is, for the Beetle, we have unbalanced force is equal to small mass times acceleration, and for the Hummer, unbalanced force is equal to a big mass times acceleration. And these, the amount of force is the same, right? So that means a smaller mass is going to have to be multiplied by a bigger acceleration to get the same number as when I have a big number times that acceleration, right? Because these two things are equal. So if you think if this number is like 50, for example, well, if the mass of this one is like 5, then this would have to be 10. And if this is the same force, 50, if the mass of this is 10, then the acceleration would only be 5, because these things multiply to that same amount of force. So the thing that we want there to be something different when like really big thing collides with much smaller thing. We want something to be different. The acceleration is different, right? Because of that mass times acceleration. So which vehicle will experience the greatest acceleration? The Beetle. The Beetle has greater acceleration. Discuss the following in terms of impulse and momentum. Why are padded dashboards safer than hard dashboards in automobiles? And what does that have to do? Like, oh, well, they're softer. Sure, yeah, but what about the physics? What's happening here? Unbalanced force. Change in time equals mass times change in velocity. So a padded dashboard, if you imagine somebody will have like a slow speed collision. This is an overhead view of a car that's going this way, and it's going to crash into this wall here. We'll go fairly slow so nobody gets severely injured. And why this person's going to crash after the car crashes here into this padded dashboard versus hard dashboard. So what can we change? If you're in the business of trying to make cars safer, you might be staring at this equation and thinking about, okay, what can I change here? If this car crashes into this wall, this change in velocity, it's going to go from however much velocity it has down to 0. And there's nothing you can do to change that. You can try, you can put up speed limit signs and beg people to drive slower, but once the collision is going to happen, it's going to happen, and there's nothing you can do engineering-wise to change this. It's going to go from all the velocity it has down to 0. The mass of the person in the car, there's nothing you can do about that either. You can tell people that they should all go on a diet before they get in a car, but I don't think that's going to work. So these things you can't change. From the point of view of the car safety engineer, that is what it is. How about on this side? What can you change? Well, we're trying to manipulate these things. You can't directly affect this. What you can try to do is you can try to maximize the amount of time here, so that will minimize the amount of unbalanced force. Because these two numbers have to multiply together. They're going to multiply together to be something that we cannot change. So if you can push this number up, that's going to push this down. That's where the engineering, that's where the safety improvements come from extending the amount of time it takes for the person to stop. And that's what the padded dashboard does. It makes it take a little bit longer time for the person to stop. So I'll just say it like this. We're trying to maximize the amount of time so that we minimize the unbalanced force. Why are nylon ropes, which stretch considerably under stress, favored by mountain climbers? Well, it's actually the exact same answer as the rope stretches. So we're talking about in the situation where a climber has fallen and the climber is going to get stopped by the rope that's tied to them. So as the rope stretches, that amount of time it takes them to stop is maximized, instead of like a non-stretchy rope where they're falling, and all of a sudden, doink, they stop very, very suddenly. If they stop very suddenly, if this is very small, then this is going to be big, and we want this to be as small as possible. So delta T, so the unbalanced force on them is minimized. Part C, when starting a heavy train, why will engineers sometimes back up, stop, and then proceed forward? So I'll try to show you with 3 little train cars. See if I can make a decent picture to explain this. This is a very practical application of this. So let's say the train cars are hooked together. They're hooked together by these hooks. That's why they're called hooks. Oh, that didn't quite work. Okay, so let's say there's no slack. In other words, what do we mean by slack? We're talking about like the 2 hooks are already like hooked like this. They're not like this where there's like a little bit of room to move before they come in contact. This would be like some slack where they're not hooked, they're not touching each other yet, and then no slack would be they're already like tight like that. So got no slack, no slack. So if the train is going to start to move this way, then the engine must accelerate all the cars at the same time. But I'm going to try to exaggerate here. Let's say there's some slack here. That's my best drawing of them not touching each other yet, so there's a little bit of room there. If they're not touching yet, like this, then you can kind of imagine what happens when the engine, the car up at the train car up at the front, it's called the engine, right? When that one starts to go forward, it only has to accelerate this one for a short distance, but there's a little bit of distance while it's just accelerating this one, and then there's the clang, then these ones link up, and this starts pulling that one, and you get kind of a collision there. And then those two moving together are going to accelerate this one, and so on. So at the very start, the engine only has to accelerate the first car itself, I guess, right? And then you get a whole bunch of little collisions down the way. But it doesn't have to start all of them from rest. So the first car, probably, I'm assuming that first car is itself, right, is the engine. And then we get a bunch of little collisions down the way. But the advantage of that is that one, you got that moving without having to get the entire thing moving, and that all those little collisions down the way, you already have that first one moving. So it's going to be easier to get it moving. It's not going to be, like, once the whole thing gets moving, well, nothing has changed then. It's still going to take the same amount of power to move that whole train down the line, but it's much easier to get started this way. So engine only needs to accelerate the first car, and then there's a series of collisions. And I was forgetting how many L's there are in collision. I'm going to go with 2. Hope that's right. You can check.